Okay, so we're gonna do metals today. So let's go through metals. Okay, so I'm going through your textbook pages. So we're gonna start at page 218. Okay, so we are going through the chapter of metals. The first part, 13.1, we are looking at the idea of metals and alloys. So before we can talk about alloys, we need to understand in terms of pure metals, what are their general properties. Okay, so some of the physical properties of, I use the word pure metal. Okay, instead of just metals, I'll use the word pure metal. So first thing, metals are good conductors of heat and electricity. I need to take note of this. Heat and electricity comes together as a pair. Okay, so please don't just write down good conductor of heat or good conductor of electricity. Make sure you have both of them. Okay, so this is the first general property of metals. Now, why are they able to do so? Okay, the key idea here is the outer electrons are able to move freely within the metal lattice. Okay, now within the metal lattice is a bit chima, so actually if you ask me, my suggestion is remember that the outer electrons, okay, let me zoom in a bit, are able to move freely. Okay, so why are metals good conductor of heat and electricity? Just say that the outer electrons are able to move freely, and that itself will be able to be good enough for you to explain why they are good conductor of heat, good conductor of electricity. So that's the first physical property of pure metal. The second one, okay, is that metals usually have high density, that's why they sink in water. They have also high melting and boiling point. So this three comes together, okay. So normally when you state a physical property of a pure metal, you will put these three together. Okay, now the question is why do they have high density, high melting, and boiling point? Key idea, okay, large amount of energy required to break the strong metallic bonds. Okay, I say again, why do they have high density, high melting, and boiling point? It's really because the metallic bonds are very strong. So the particles are actually very strongly attracted to one another. As such, we need a large amount of energy. Okay, and that's why they have high density, high melting, high boiling point. So this is the second physical property of metals that you need to know. And the last one is that pure metals are malleable and ductile. So what is malleable? Malleable means that you can actually hammer them into different shapes. That's the idea of malleable. So you can hammer the metal and it can form different shapes. Now, what exactly is ductile? So you can actually pull it. So drawn into wires without breaking. Drawn actually just means pull. So you can pull the metal into wires, okay, without it breaking. So that's what we term as ductile. So malleable and ductile comes together as a pair. Okay. Now, why I keep emphasizing on as a pair is really because most students, when they write down the physical property of metals, they tend to write malleable as one property, ductile as another property. Okay, and that itself you will not get the full marks. Okay, because this two is actually 1 point. This three is actually 1 point. This two over here is actually 1 point. Okay, so I just need to take note of that. Now, so these are the three physical properties of pure metals. Pure metals. Okay, now let's go on to the next part. So question is why pure metals are not widely used in industry. You don't generally use pure metals. It's really because they are soft. Okay. Second thing is they can react with air and water. Okay, and wear away or corrode easily. Now, when iron react with air and water, when iron react with air and water, right? We see this phenomenon daily, quite regularly in our lives. We actually call this rusting. Okay, so pure metals generally are soft, okay, because the atoms are packed regularly in layers. You can hammer them. Later on, we will see a little bit. Pure metals also, they rust quite easily. So therefore, we will tend to use alloys. Okay, before we go into the idea of what alloys are, I want us to go back to this part here. Okay, look at this. Look at the two diagrams over here. I will need you to see that in figure 13.2a, this diagram over here, okay, the atoms of the metals are very regularly packed. Okay, so the atoms of metals are packed regularly in layers. If you only hammer at the top two layers, what's going to happen? You realize that the layers are able to slide over one another easily when the force is applied. So this is the issue about pure metals. Pure metals are soft really is because of the idea here that they are regularly packed. When you hammer them, they will actually slide over one another. Okay, so pure metals are soft. So generally in real life, we don't use pure metal. We actually use what we call an alloy. Okay, so what exactly is an alloy? Alloy is a mixture of metal, okay, a metal with one or a few other elements. Now, the word here, right, seems to be like emphasis that, you know, I can only use one metal. It's not really true. If you ask me, generally what I would classify an alloy is actually a metal mixed with other elements. Okay, other elements. It can be one element, okay, or more than one element. Later on, you'll see some examples. Okay, so metals are often used in the form of alloy. There's actually four positive. I say again, there's actually four positive reasons of why metals are used in the form of alloy. Why do you want to mix pure metals with other elements to form an alloy? First, by making it an alloy, you actually make the metal harder, stronger. Okay, you actually make the metal harder and stronger. Now, once they are harder and stronger, okay, you are able to sort of like use them to reinforce buildings and stuff like this. Okay, or you can make them into instruments like this so that they are less fragile. Okay, they can withstand more knocks. Okay, especially students like to knock the instruments here and there and spoil it. Okay, next, alloys actually also help to improve the appearance of metals. Okay, so there's this thing called pewter. Now, all these examples, don't worry, you don't need to know. You just need to know the reasons why alloys are used. So actually, you can improve the appearance of metals. So one example is this thing called pewter. It's an alloy. It actually makes the metal more shiny, more beautiful. Okay, that's actually what alloys can do. Next, alloy can also lower the melting point of metals. So it melts easily, means that I need to use less energy for it to melt. So example is solder. So solder is very important because it's used to connect the metal parts together. Okay, so if I can lower the melting point, it's very easy for me to connect the circuit using soldering. Last one, okay, make metals more resistant to corrosion. So cupro-nickel, okay, actually is used in our coins. It allows the coin not to be rusted or corroded so easily. Okay, so make them more resistant to corrosion. Now there are many other examples, okay, of alloys for each of these. Okay, now, but I don't need you to go and memorize the example. I just need you to memorize this four. You just need to know this four. One, two, three, four. So why are alloys used instead of pure metals? It's really because of these 4 points here. Now do take note. Um, it doesn't mean that every time once I got alloy, I'll have all these 4 points included. Different alloys make use of the reasons here. So cupro-nickel is resistant to corrosion. Right, but does it actually lower the melting and boiling point? It's not a confirmed thing. So I need you to just take note. Okay, depending on what things you're mixing with the metal, it will give different properties. Okay, but you don't need to remember what's the mixtures. Okay, now, but the thing is, this one, I'm sorry, this one always like to come out, so I need to remember. So why are alloys stronger and harder than their constituent metal? Or why are alloys stronger and harder than pure metals? Okay, this is one very common question that likes to come out. So I need you to know it. Okay, so first thing is that in alloy, the atoms of the different elements, so atoms of the different metals or element, they got different size. So you can see here, these blue color dots, or all these blue color dots here, are the pure metal atoms. Okay, are the metal atoms. When you introduce another element, you realize that they destruct. You can see here, the regular pattern of the blue color balls are actually disrupted. Okay, you disrupted them. So in alloy, the atoms of different metals or elements, because of their different sizes, they actually disrupt the regular arrangement of the atoms in the pure metal. Okay, now So what has this disruption has to do with the alloy being harder and stronger? So now if the regular arrangement is disrupted and then I apply a force, will they be able to slide over easily? Answer is no lah. Okay, answer is no. So therefore, if I'm able to disrupt the regular arrangement with the introduction of the atoms of different sizes due to their a different metal or different element, okay, now the alloy is stronger and harder because the atoms of different sizes cannot slide over each other easily when a force is applied. I realized out here I got missing words. Okay, so the atoms of different sizes cannot slide over each other easily when a force is applied as a result. Okay, so when a force is applied. As a result, an alloy is actually stronger and harder. So normally if this comes out in the O levels or N levels, this will actually be about 2 marks. Okay, when you need to explain regular arrangement disrupted. Secondly, because of the disruption in arrangement, okay, it's harder for the atoms to slide over one another. Okay, so that's for this part here about alloys. Okay, so in terms of the 13.1, we're actually really just trying to find out what pure metals really are talking about. Then next, once we know what a pure metal is really about, then we focus on the alloy part. Okay, so the key idea behind 13.1, these are the 3 physical properties of metals. Okay, next, 2 and 3 comes together. It's really about how alloys are stronger and harder. Okay, then the 4th part is the reasons for making alloys. Okay, so this is what we have covered in 13.1 so far. Now let's go on 13.2, the reactivity series. So this is the one that you all remember. Okay, so let's before we go into all of this, there's the mnemonic to remember the sequence of metals. So the one that I introduced to all of you is actually pop stars can make all calm zombies in town lose his cool SG. Okay, so this is the whole series here. What does each of these first alphabet tells you? Okay, they're actually the elements. So I'm going to write in blue here. So P stands for potassium, S for sodium, C for calcium, M for magnesium, A here for aluminium. Okay, this one here is not really a metal. Okay, it's actually carbon. Carbon is actually a non-metal. Z for zinc, I for iron, T for tin, L for lead. H is not really a metal, it's actually hydrogen, it's actually a non-metal. C for copper, S for silver, G for gold. Okay, so this is the whole series here. Okay, we'll be touching on it, focusing and re-looking back at this a little bit more later on. Okay, so this is the sequence I need you all to take note of. So what is this whole reactivity series about? So the top here, potassium, is actually the most reactive amongst the whole series here. All the way at the bottom, gold is actually the least reactive metal. Okay, so that's what this whole reactivity series is about. So, so first things first, let's go on to what is being mentioned here. Okay, determining the order of reactivity of metals. Okay, so it's useful to arrange the metals according to how reactive they are. So scientists have worked out a list called the reactivity series, which is what we are seeing here. Okay, in the reactivity series, metals are arranged from the most reactive all the way up there, potassium, to the least reactive all the way down here, which is gold. Okay, now the thing is this: how do scientists determine how reactive they are? So they actually look at the reaction of the metals with cold water, how the metal react with steam, and lastly, how the metal react with dilute hydrochloric acid. So before we go into looking at how the metals react with cold water, steam, and dilute hydrochloric acid, let's zoom in on the reaction themselves first. So first thing, metals can react with water, metals can react with steam. Okay, the products for each of these is slightly different. So metals, can they react with cold water? They can. So when metal react with water, or they use the word cold water, you actually get a metal hydroxide plus hydrogen. Okay. Now, if the metal reacts steam, instead of a metal hydroxide, actually you get a metal oxide. So you realize if you use cold water versus you use steam, the product is different. Okay, the product is different. So I need you to take note of this. Okay, so metal plus cold water, you actually get metal hydroxide plus hydrogen. Metal with steam, okay, you actually get metal oxide plus hydrogen. Okay, and the reactions here, okay, I don't need to remember this picture, okay, so don't worry about this. Now, what you need to remember is actually this part, this table over here. Okay, how do each of these metal reacts with cold water? Okay, so for this box is how, so for this box over here is actually how potassium reacts with cold water. This box over here is actually how the metals, potassium, sodium, and calcium react with steam. Okay, that's how you read these. So for cold water, you realize that only the first four elements react with it. Okay, only the first four elements, potassium, sodium, calcium, and magnesium, reacts with cold water. So I'm going to write it down here, okay, on my notes. So I'm just going to write out the whole reactivity series again. So pardon me. Okay, at this point, you can try to recall what is the whole reactivity series. Pop stars can make all calm zombies in is sorry, I shouldn't write zombie, should write zinc. My bad. Okay, zinc. Pop stars can make all calm zombies in town lose his cool SG. SG stands for silver and then gold. Okay, now, so as what we've seen in the textbook, only the first four react with the cold water. Okay, first four react with cold water. So 1, 2, 3, 4. This four reacts with cold water. Okay. Now, what is the product of it? You can see here the metal plus the water, cold water. You actually get the metal hydroxide plus hydrogen gas. So all of them will always produce hydrogen gas. Okay. Now, look at in order. Potassium reacts very violently. Sodium reacts violently. So obviously, based on the two description, you know that potassium is definitely more reactive than sodium. That's why potassium is above sodium because it's more reactive. Comparing sodium and calcium, you can see sodium reacts violently, calcium only reacts readily. Okay, so the word violently tells you it's still quite a strong reaction. Okay, so you can see that's why sodium is definitely higher than calcium. Last one, magnesium reacts very slowly with cold water. So readily versus very slowly, you can see why calcium is more reactive than magnesium. So that's why they will use the reaction. I can use reactions to determine how reactive the metal is. So just take note of that. Now, steam is actually just very, very hot water, but in the gas form somewhere. So you realize that, oh, if it is steam, potassium, sodium, calcium will react explosively. Okay, so it's a very, very dangerous reaction. Magnesium will react violently. So you can see that's why it's less reactive than calcium. Zinc will react readily, while iron actually reacts slowly. So you can see the description itself goes from a more intense, more violent reaction, all the way down to a relatively less violent reaction, okay, which then describes as slowly. So based on this, we know all the way until iron, it can react with steam. So let's go back to this. All the way until iron, it can react steam. So from, let's use a different color. So from the first element all the way until iron, okay, reacts with steam. Okay, so what you realize is that okay, yes, How many react cold water? 4. How many reacts with steam? The first 4 plus another 4. So which is actually equals to 8. So 4 react cold water, the first 4. How many reacts with steam? Okay, is the next 8. Okay, it's the first 8. Okay, until iron. And now let's go back. Okay, so what you realize is that lead, copper, silver, all this no reaction. That's why anything below this, so only the first 4 react cold water, hence aluminium all the way down to gold doesn't react cold water. This 8 reacts with steam. Anything from tin to the gold, it doesn't react steam. So that's how you go about reading this little drawing that I have made here. Okay, so we have gone through reaction with cold water, reaction with steam. Okay, now for the reaction with steam, I need you to take note of one thing. Okay, it is what I've mentioned before, but I'm going to mention it again. Please take note of the difference here. Can you see when the reaction is with cold water, I get hydroxide. Okay, so that's why calcium hydroxide, magnesium hydroxide, sodium hydroxide, potassium hydroxide. But when I react with steam, okay, it gives a different one. Can you see this oxide? It's not a hydroxide because it's only O, it's not OH. Same thing here, you can see oxide, zinc oxide, Fe3O4, this iron oxide. So you can see here when I react the metal with steam, the metal, I let it react steam, I don't get hydroxide. I actually get an oxide instead. So you must be able to differentiate between these two. Sorry for nagging on this, but this is generally what people tend to miss out. So be careful on it. Last one is the reaction of metal with dilute hydrochloric acid. Okay, or I should say reaction of metal with the acid itself. So when I have metal reacting with acid, what you're going to get is a metal chloride. This is actually a salt. So I actually get salt and hydrogen. If I use sulfuric acid, I'll get metal sulfate. If I use nitric acid, I'll get metal nitrate. So take note, okay, when you have hydrochloric acid used, the salt name will end with a chloride. So this is the acid that you use. This will be the salt form. If I use sulfuric acid, I will actually get a sulfate salt. And if I use a nitric acid, I'll actually get a nitrate. So do take note of the name of the salt, okay, based on what acid you use. So if I'm using hydrochloric, you realize that the salt name given will actually be a chloride. Okay, so take note. Now, back to this. Which elements can actually react with dilute hydrochloric acid? So based on all this, you realize, exactly the same. Okay, but I want us to look at the bottom here. Lead should react with dilute hydrochloric acid since it's more reactive than hydrogen. What does this statement mean? This statement means that actually for the thing to react with acid, you just need the element to be higher than hydrogen in the table, which means for acid, right, the potassium all the way until lead. All of this actually can react with acid. So this is actually a 4 plus 4 plus 2, which is a 10. Okay, so let me decorate a bit more. So this one is until here. This one, I think quite clear. Okay, so first 4, 4 plus another 4, 4 plus 4 plus 2. So to react with acid, actually from potassium all the way to lead can react with acid. However, why is it that in this table, lead, they say, lead here, how come never say it can react? So the key idea here is this. When lead touches hydrochloric acid, okay, so imagine if this is a piece, this is a beaker, I got lead over here. When I throw acid in, okay, acid, to be more specific, hydrochloric, and this is lead metal. Okay, when they start reacting, it will form this powder, okay, this solid around it. This red color solid that's being formed is actually lead 2 chloride. So lead 2 chloride will actually form around the lead, okay, because it's an insoluble salt. Since it forms around it, okay, you realize the lead is no longer exposed to hydrochloric acid and hence it can't react anymore. Okay, so this is something like a sideline info, okay, but okay, all this sideline info, do remember, all the way from potassium to lead, they are supposed to be able to react with acid. Okay, so based on the reaction of metal with cool water, steam, and dilute hydrochloric acid, we can actually place the metal in order of their reactivity. So this is what is given in your textbook, but you realize I've added some additional elements, okay, within here, and hence we got this. Pop stars can make all come zombies in town lose his cool SG. Okay, so that is the order I need you to remember and really just keep it in your head. If you want, you can go and test your friend once in a while to just get them to stay fresh in terms of the reactivity series. Okay, so let's scroll down. Now, so what is the point of using the reactivity series? What's the point of knowing it? So by knowing it, we can actually predict the behavior of the metals based on its position. Okay, next, we can also use to predict the position of an unfamiliar metal from a series of experiments. So for the first one, okay, actually it's quite simple. I can explain using here. Now imagine I found element X. Element X. I say it reacts very readily with cold water. X reacts very readily with cold water. Now you look at the description here. Very violently, violently. Readily, very slowly. Based on all this description and looking at what I described X as it reacts very readily, we know X must definitely be here, above calcium, because calcium is readily, but X is very readily. But it is below sodium because sodium reacts violently, whereas X is just very readily. So you realize by being able to describe the reaction, you're able to fit it within the reactivity series. So that's what they meant by you are able to predict the behavior of a metal from its position, predict the position of an unfamiliar metal in the reactivity series, okay, based on the experiment results. So let's look at some examples here. I want to look at example 3 because this is very common. Okay. Now, for you to be able to do all this, okay, I realize there's one reaction that's not listed here. Okay. Yeah, there's one reaction not listed here. So let me write this down. Okay, now, this is what we call the displacement reaction. So for the displacement reaction, this one is the one that I mentioned to you. Okay, this is what I also call it the sexy reaction. Now, what is this sexy reaction about for those of you who are not so clear in terms of the displacement reaction? Okay, take note, the key idea here is a more reactive metal, okay, will displace another metal, another less reactive, will displace a less reactive metal, okay, from its compound, okay, from its compound. So a more reactive metal will displace a less reactive metal from its compound. So let's look at some of this example here. So I want to use this example of magnesium. I want to use this example here. Magnesium plus copper 2 sulfate. What will I get? Will there be a reaction? So you can see copper is attached to sulfate. Copper is attached to sulfate. Copper is a metal. Huh? Magnesium came into the picture. So you got to ask yourself, which is more reactive? Okay, if magnesium is more reactive, magnesium will kick the copper out. Okay, magnesium, sorry, wait for this. Okay, so as I say again, magnesium, if it is more reactive, it will actually kick the copper out. So we got to ask ourselves, okay, comparing magnesium and copper, what is their reactivities? Where are they in the reactivity series? So go back to here, realize magnesium is actually number 4 in this whole series, whereas copper is number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Number 12 in the reactivity series. So obviously magnesium is higher. So if magnesium is higher up, what's going to happen is that magnesium will kick copper out. So copper now will be stranded, okay, on its own, and magnesium will be attached, okay, to the sulfate. So the more reactive element will actually kick out the less reactive element. That's the key idea, isn't it? Okay, so whenever you see a tick like this, it means that magnesium has displaced copper. Okay, so this is all the salt solution of the metal. So copper sulfate, I put magnesium in. Magnesium can kick it out. So obviously magnesium is more reactive than copper. Iron, I put with copper sulfate. There is a reaction. So tick, that means iron more reactive than copper. Next, zinc, I put in copper 2 sulfate. Zinc can also displace copper. So we know that magnesium, iron, and zinc is more reactive than copper. We all know, based on this, we all know. But in actual fact, we also have our pop stars can make all comes of this. We have the reactivity series to determine whether the element is more or less reactive. But let's say if we do not know, we can actually use this. Next one, magnesium nitrate. You realize when I put copper, iron, and zinc in, none of them could displace magnesium, which tells me magnesium is the most reactive one. Copper, because can be displaced by all, copper must be at the bottom. Now I'm left with iron and zinc, which is going to be in the middle here. So magnesium can displace iron. Copper cannot, but zinc can. So what does it tell me in terms of the reactivity series of zinc and iron? So zinc, if it can kick iron out, that means zinc is more reactive. So zinc must definitely be above iron. As such, this is the order of the reactivity series. Magnesium being the most reactive, copper being the least reactive. So that's how you can interpret this kind of table here. And obviously the last one, zinc nitrate, you can see only magnesium can displace it, copper and iron cannot. So this tells me that my table here is correct. So as I mentioned, example 3 is a very classic one. Sometimes in MCQ it comes out, sometimes in paper 4 it comes out as a structured question, but they like to give you this kind of table, ask you to interpret in terms of coming up with the reactivity series. Okay, so take note of this, take note of this. Okay, now, so based on all that, okay, I need you to know the reaction of the metals with cold water, with steam, and then with acid. Okay, it's important to know this. Can? Okay, so next up, let's go on to the next one, which is 13.3, extracting metals. So what we have covered so far is actually metals versus alloy. So previously in 13.1, we covered metals versus alloy. Okay, to be more precise, it's pure metal versus alloy. In 13.2, we covered the reactivity series. And we look at this type of reaction called the displacement reaction. And now in 13.3, we are looking at how to extract metals. Right, how to extract metals. Okay, so in terms of extracting metals, okay, why must we extract them? It's really because in real life, okay, most metals exist in the form of ore. What is an ore? An ore is a compound of metal, usually oxides, sulfides, chlorides, or carbonate, or it mixed with large amount of earth and rock. So example, when you see this, it is called an azurite. It's a copper ore. So you don't get pure copper inside here. You actually get copper carbonate, copper hydroxide, okay, and you must let it react with things in order for the copper in order for you to get pure copper. So in real life, you don't really have pure copper. You actually got this kind of ore. Okay, in this case, it's called azurite. It consists of different compounds of copper. So from there, you must learn how the different techniques on how you can get copper out of it. Okay. Now, there are two main methods of extracting metals from their ore. Two main methods. The first one is using carbon. The second one is using electrolysis. So how do we know when we should be using the methods? Okay, so very simple. Anything above magnesium. So the first four elements is actually extracted using electrolysis. Means I use electricity, okay, to break down the ore. So actually electrolysis is using electricity to obtain the metal from the ore. Okay, that's what electrolysis does. It's actually you are breaking down the ore so they can get a pure metal out of it. Okay. Now, why is it that this four I use electrolysis, whereas the bottom I can actually use this method called reduction by carbon? Go back to our pop stars can make all come zombies in town. What you realize is that for anything above carbon, okay, so carbon is at this point, right? Anything above carbon, okay, maybe I shouldn't use this color. Let's use pink color. Okay, let's use pink color. Anything above carbon, I cannot use reduction by carbon because they are more reactive than carbon, means carbon cannot kick them out. So all of these elements that's above carbon, I actually use electrolysis to extract the metal. But anything that's below carbon, because they are less reactive, I can use carbon to kick out the pure metals out. So all this below here from carbon, from zinc down all the way to the bottom, I can actually use the method called reduction by carbon. Okay, so back to this. So the reason why there's this split, some electrolysis, some reduction by carbon, is really because I can use reduction by carbon for those that's below carbon. Those that's above carbon, I must use electrolysis. Now, of course, the main question is, sure, why don't everything use electrolysis? We believe that if this more reactive one can use electrolysis, this less reactive one also can use electrolysis, ma? Okay, so why we don't use electrolysis for everything is really because electrolysis is actually expensive. It's actually a very expensive method, right? Because you use a lot of energy just to extract the metals out. So we will try not to use electrolysis as possible. We actually use the reduction with carbon, which is a cheaper method to get the metal out from the metal ore. Okay. Now do take note, gold is actually found naturally uncombined. That means if you got a chance to dig into a gold mine, when you dig, when you find the ore of gold, okay, no such thing at all. When you find gold, it's really pure gold. Okay, that's why you realize there's a lot of gold miners. They will tend to go to the quarry, go to the mine, and then they'll go inside. They will hit the rocks, hit until they can get pure gold out. Right? So that's because why? Gold can be found naturally, uncombined, pure metal, pure gold. Don't need to extract, easy peasy. Okay? But the rest, above here, silver included, you must use extraction by carbon. Anything above carbon, you must use electrolysis. Okay? Now, so we learn about how how we can obtain the pure metals, okay, either by electrolysis or by reduction by carbon. We're gonna go in depth into one of them. So we're gonna look at how we can extract iron from iron ore. Okay, so you learn how about the reactivity series, you learn that which one, how we can extract the pure metals out. Then now we're just gonna go zoom in to really look at how we can extract the iron from the iron ore. Okay, so this is where you have this word hematite. Okay, or some of you, if you can't really spell it right, you can actually pronounce it as Hematite. Okay, Hematite. Okay, if you can't really spell it properly lah. Now, but the main ore of iron is actually hematite. It consists of iron 3 oxide. So hematite is mainly iron 3 oxide, but it has also sand and clay mixed with it. So is it pure iron 3 oxide? No lah. It's actually iron 3 oxide with other materials such as sand and clay. Okay, so how do we really extract it? We actually throw hematite, coke, and limestone at the top of the blast furnace. Then hot air is blown from the furnace, blown into the furnace near the bottom. So three things goes in from the top, one thing goes in from the bottom. Then there's like some cooker. So you let it cook, finish already, you'll get your pure iron. Okay, how does it look exactly? It looks like this. Okay, so let me zoom out a little bit so we can see the diagram better. Okay, so it looks like a super big oven, okay, in some sorts of a sense, okay, some sort of a idea lah. So how does it really work? Okay, so what you're doing as I drawn up here, okay, three things in. So you can see the hematite, coke, and limestone is thrown in from the top. Then we actually have hot air that's being blasted in from the bottom. And this is where the reaction occurs. Maybe red is not such a good color on orange, huh? So use blue. So this is actually where the reaction happens. Okay, the hematite, coke, and limestone will react. The hot air go in will react with it. Okay, and we will get what we want, which is pure iron. Now, do take note, hot air actually consists of nitrogen, oxygen, carbon dioxide, argon. Okay, now as all the gases go in, okay, argon actually noble gas, but it's such a small percentage, let's exclude it out. These three gases that goes in, now the reaction happens here actually only uses O2 and CO2. Nitrogen is actually being released out because it's not involved in the reaction. So you can see waste gas is released, which is N2. Then somebody say, how come CO2 and CO also released? Now, do take note, although the reaction uses carbon dioxide and carbon monoxide, okay, but you can't really trap all the gas inside there. As such, as it reacts, we will actually be losing some carbon dioxide and some carbon monoxide, okay, out into the out of the reaction vessel. Okay, so just take note of that. So this is actually the what we call the blast furnace. Three things in from the top, one thing in from the bottom. Reaction occurs in the middle. So let's go into detail what is actually happening. Now, first step, carbon dioxide gas is produced. How do you produce carbon dioxide gas? Okay, you actually use the carbon, which is the coke that you are throwing in. You let it react with the oxygen, with the hot air that's coming in. This is actually from the hot air. Okay, when these two react, you actually get carbon dioxide. So first step is to produce carbon dioxide. Now, the carbon dioxide is not the main thing that's actually reacting. Okay, we actually want carbon monoxide. So how to get carbon monoxide? So first we produce carbon dioxide. Next, this carbon dioxide will actually react further with the coke. So first I use coke plus hot air to get carbon dioxide. This carbon dioxide will react with more coke and it will give me carbon monoxide. So these two reactions important, please take note of them. Okay, so step 1 and 2 is together. Key idea here is to produce carbon monoxide. Now, some of you say, sure, how to remember all this is so difficult. My suggestion is remember the equation. If you know the equation, you can actually describe it. So for example, number one, if I know the equation here, I will just say coke reacts with oxygen, okay, with hot air, bracket, oxygen from the hot air, okay, to form carbon dioxide. So you realize all I'm doing is actually just to describe the equation. Same thing, I can also write here, coke react with the carbon dioxide to produce carbon monoxide. So this equation here, actually also you can just describe it to get your marks. Okay, so blast furnace description, actually if you know the equation itself, is a lot easier to describe it. So the first two steps are the important step because you need carbon monoxide. This guy here is the main star. Okay, carbon monoxide is the one that helps you to get the pure iron. Next, step 3. Hematite is reduced to iron. So the iron ore reacts with carbon monoxide. So Fe2O3 reacts with CO. You actually get molten iron and carbon dioxide. Okay, molten iron and carbon dioxide. So please remember this equation. It's not easy to balance it. So my suggestion is you might want to just memorize the whole equation, okay, together with all the balancing numbers. 3, 2, 3. Okay, 1, 3, 2, 3. Okay. Now, do take note, iron form is molten and runs to the bottom of the furnace. So whenever you see the word molten here, it just means it's a very hot liquid. And because it's a liquid, you know that it will definitely flow down the blast furnace. Okay, now, so at this point, this part here, this is actually the iron. Iron is at the bottom layer because it's a liquid, it will flow all the way down. And when there's a tap over here, when I switch on the tap, the molten iron will actually flow out. It's quite a cool reaction actually. Okay, next. Okay, now this is actually done by engineers. So they realize that, you know, the iron ore has a lot of sand, a lot of clay. I need to get rid of the sand and the clay. But if I keep throwing more and more hematite and try not, and I don't get rid of the sand and the clay, my whole thing is going to jam up. Okay, but to stop the whole thing here is also very expensive because why? I heat it up until so high temperature. After that, I let it cool down, get rid of the sand, then I must heat it up again. So it's also a waste of resources to cool it down, to get rid of the sand, and then heat it back up again. So what the scientists did was very clever, very smart. So they realized that I can remove the impurity. Okay, the impurity that we want to actually remove is the sand. Okay, the sand is actually the silicon oxide. Okay, silicon dioxide to be more precise. So what they do is, why do they throw the limestone? If you realize from the top here, number 1, number 2, number 3, limestone is not used at all, even though we throw limestone in. So what exactly is the use of the limestone? It's actually to remove the impurity. First step, the limestone actually decomposes. So you heat up the calcium carbonate, you actually get calcium oxide and carbon dioxide. Okay? Now, the most powerful thing is actually the calcium oxide. So first part is actually just heating up the limestone so that it decomposes, okay, to this. So this is our first equation for impurities removal. The second step is the real stuff. You actually use the calcium oxide, okay, you let it react with the sand, which is your silicon dioxide, and actually you get this thing called the calcium silicate, which is known as slag. Now, what is so interesting about this reaction is actually calcium oxide is a solid, silicon dioxide is a solid. So both of them are actually solids. It's very hard to clear solids from a reaction vessel. You must dig it out and stuff like this. It's not easy. But when these two things react, you realize slag is actually a liquid, which is like, wow. Because it is a liquid, you realize that it will be formed as a layer like this. This is actually your slag. Let me use a different color. This is actually your slag. Now, why is slag on top of iron? Because slag is less dense. Iron is more dense. Or you can think of it as denser, either one, denser or less or more dense. Not more denser, more dense. So because slag is less dense than iron, you know that slag is on top. And with a tap like this, I can also turn on the tap and the slag will actually flow out. So in this whole reaction, I don't need to stop the thing at all. I just need to turn on the tap and all the liquid will flow out. I can get the iron which I want, I can get the impurities out, and the reaction can keep going on and on and on and on. Okay, so this is actually the interesting thing about the blast furnace. It's used to extract iron from the iron ore, which we know as hematite. And the reactions involved actually got 5. So let's recap a bit. First reaction is over here, carbon plus oxygen, give me carbon dioxide. Second step, the carbon dioxide form reacts with more coke to get carbon monoxide. Third step that you actually get is here, which is the carbon monoxide reacts with iron 3 oxide to give you molten iron and carbon dioxide. So this is the third step, third reaction. Then the fourth and the fifth is really just to get the impurities removed. Okay, so these are the 5 chemical reactions that happens in the blast furnace. Okay, so I repeat again, these are actually the 5 reactions that happen in the blast furnace. By remembering the equation, you can actually be able to describe the reaction itself also. So just take note of it. Okay, so this is just a summary of what we highlighted in terms of the metal extraction. Okay, now 13.4, we go on to the second last part, we highlight rusting. Now, rusting is just a very small component within the syllabus itself, but when it comes out, if you ask me, I think it's what I call free marks. It's not difficult at all. Okay, so first thing you need to know is that rust or the corrosion of iron, okay, rusting is the corrosion of iron. Sorry, rusting is the corrosion of iron. Okay, now the equation here, don't need to memorize. You look at this is so cheap, forget it. The main thing you need to know is for rusting to occur, you need oxygen and you need water. So you need these two to be present in order for rusting to occur, oxygen and water. Okay, so I want us to look at this investigation over here. Now, this investigation is important because some of the things here actually helps you to understand what you're trying to remove from the conditions of rusting. For example, okay, look at the test tube A. Okay, I put nails inside each of these. Now, then you realize they put all these different things together, right? First things first, what is the purpose of oil? What's the purpose of boiled distilled water? What's the purpose of cotton wool? Anhydrous calcium chloride? Okay, so on and so forth. So let's go through one by one. First thing, oil. Oil, what's the purpose of it? Is to prevent air from dissolving into the water. Okay, so oil actually prevents air from going to the water. Next thing, why do I want to boil the water? So boiled water is actually to remove the oxygen. Remove oxygen from water. So in actual fact, in test tube A, my nail wouldn't rust because why? With the oil and with the boiled distilled water, there's no oxygen in test tube A. So in test tube A, what they're trying to do is to make sure that there's no oxygen. Okay? Look at test tube B. I got cotton wool. Okay, is to prevent water. So what's the purpose of the cotton wool? Is to prevent water droplets from reaching nails. Okay, that's the purpose of the cotton wool. Next, I got this anhydrous calcium chloride. What exactly does this fella do? This fella here actually absorbs water moisture or water from the air. Okay, so if you absorb water from the air, actually you are keeping the air dry. So in test tube B, you realize with the cotton wool with the anhydrous calcium chloride, there's no water present in test tube B. Test tube C, you realize it's distilled water, there's no covering here. So this one, tick, got oxygen, got water. So obviously test tube C, you know sure rust one. Test tube D, there's no oil, no nothing, never boil, so you know that tick got oxygen. Obviously, this is a solution, so tick, there's water. Lastly, actually sodium chloride is a salt. Wow, add salt some more. So what's the thing about salt is that salt actually speeds up rusting. That's one thing I need you to take note of. I have one star here, is that salt actually speeds up rusting. Okay, salt actually speed up the rusting. So if you look at all the results, okay, as I mentioned, A got water but no air. No air, actually you are focusing on no oxygen, so no rusting. B, as mentioned, there's no water, so there's no rusting. C, confirm will rust because of water and air. D, I already said salt will speed up the rusting. So therefore, with water, with air, with the salt, the nail rusted heavily. Okay, so this is actually a point that you need to take note of, okay, in terms of rusting. Now, how to prevent rusting? Just need to remember these three methods. You can either coat the metal with paint or grease, you can coat it with plastic, or you can do this thing called electroplating. Electroplating is actually just coating with another metal. Okay, possibly coating with another less reactive metal. So by doing this tree method, you are actually able to prevent rusting, okay, or reduce the chance of rusting. Okay, okay, so that will be it. Okay, for rusting part. Lastly, we're gonna go on to this final last part of metals, about recycling metals. Okay, normally you realize this doesn't really come out in the exam, like you got to write a lot. The key idea here about 13.5 is really to appreciate the idea of metals. Okay, the appreciate metals a little bit more. Okay, a lot of things around us are made of metals. As such, as we study metals, we also talk about why not just let you all know that metals are actually quite precious. Huh? What do I mean by that? Okay, metals are actually what we call finite resources. That means they are limited. Okay, they are limited. So if we keep spamming metals, never bother whether we got enough or not, and just anyhow use them, we will come to a point in time where we got not enough metals. Okay, so metals being a finite resource is something we need you to remember, because we want you to care for the world. We want you to know that metals are finite. You don't use them wisely, you're going to run out of metals. Okay, so that's why it's important to recycle metals. Okay, as I said, it's important to recycle metals. Now, what are the advantages of recycling metals? So, metals, obviously, when you recycle, you conserve the resources. That means I don't need to keep mining to get the metal. I can actually, based on the current existing metals, as we recycle them, we reuse them. So, recycling helps to conserve the natural resources. Next. Hello, Sabine? Yeah. Okay, so recycling helps to reduce the environmental problems related to extracting metals from their ore. Okay, so what do I mean by recycling helps to reduce environmental problems? Because sometimes when you extract the metals from their ore, okay, it actually, when you do the mining, it actually, after the mining, plants and animal life can no longer be present there. So actually you damage the environment when you are mining the ores. So it's actually not that good. So as mentioned also in here the diagram, when you got 100 tons of ore, actual fact only 10% you can produce your metal. The other 90% is actually wasted. Okay, they're actually like your waste. So we can either use it to fuel land and whatsoever, but you realize I've actually dug out, okay, I've digged away 90% of things. That's really not what I want. Okay, so it's quite waste if you ask me. I damaged the environment and I still need to now replace this 90 tons of waste. Okay, so just think note of that. And lastly, recycling actually saves the cost of extracting metals from their ore. Extracting metals from the ore actually can be quite expensive, especially if you are using electrolysis. So don't take note of that. Okay, so one, two, three. These are the advantages of recycling metals. Now, in terms of the issues relating to recycling metal, sometimes recycling metal we got cost issue. Doesn't mean you recycle is always cheaper. Okay, actually recycling sometimes can be even more expensive because you need to transport the scrap metals and stuff like this. So there are costs involved that people may not want to pay. Next, okay, social issue is because we don't have the habit of recycling things. So you realize you want to recycle, but people don't want. Last one, recycling can actually also cause pollution problem. Okay, what do we mean? When as we recycle stuff, sometimes we will produce harmful materials. Okay, example, in the recycling process for car batteries, the batteries are melted and harmful gases are actually produced. So in the midst of recycling, actually harmful gases are produced in the midst of it. Okay, so doesn't mean recycling is always good. There are also issues involving recycling also. So it's about balancing the pros and the cons when we look at mining for metals versus recycling metals. Okay, so that's really the last part over here. What do you need to memorize in this whole last part? Actually, you don't need to memorize. You just need to know that metals are finite. The rest of it is really common sense. If you ask me, all these advantages, okay, all these issues, they're actually just common sense. I think you all can also figure it out. Okay, so that's all for metals ready. Okay, in summary, you can actually look at map it that's found on page 238. I thought the map it itself is actually quite a good summary in terms of what we have actually covered. So metals, the structure, what are alloys. Next thing, we went on to the reactivity series, most reactive on the top, least reactive at the bottom. From the reactivity series, we talk about how we can extract metals, okay, but we focused on iron, which then we look at the blast furnace reaction. Okay, the reaction in that big cooker is called the blast furnace reaction. And lastly, we look at rusting and recycling. Okay, so that was the 5 portions that we actually went through tonight, and we have actually covered it in 1 hour. Okay, so metals is not a very difficult chapter. It's just once you get a hang of the concept, you know the reactivity series, actually it's not too tough already. Okay, so that's all. Let me stop the recording.